Hello everyone. In this video we are going to talk about alternating series. So what is an alternating series? So here we're going to have our an be a positive sequence, so all of these are positive numbers. Then an alternating series is of one of these two forms, basically -1 to the n or -1 to the n plus 1 times our an. So why? Well, the fact that all of the an are positive means that multiplying by -1 every time is going to switch our signs, right? And so the two cases arise from whether we want our first term to be positive or our first term to be negative, right? So here, first term is negative because we start with an odd power of our -1, and here our first term is going to be positive. Okay, but from there on out, we're just going to switch sign every time, and hence alternating series. So we've actually already seen several examples of these. So first, this is one of the first series we saw together overall, was -1 to the n by itself. So here, secretly, right, our an is 1 for all n, but we don't need to write that, so we just have our -1 to the n, and this is alternating, right? This looks like -1 plus 1, -1 plus 1, and so on. So we found out that this one diverged, right? So our partial sums varied between -1 and 0. -1 for the odd partial sums, 0 for the even partial sums, and thus never approached a single value, so our series diverged. We've also seen some geometric series that happen to be alternating. So this series, for instance, doesn't look like it's in that form necessarily, but if we pull out a -1 to the n, then we have -1 to the n times 1/2 to the n. And so this would be our an. All of those are positive, so this fits. And of course, we know this converges because the absolute value of our r is less than 1. And we know that that means this geometric series converges. So let's spend some time on a new example. So let's look at the alternating harmonic series. So we, of course, know the harmonic series, right? The sum of 1 over n from n equals 1 to infinity. And we know that this diverges and has been kind of a very nice example for us throughout dealing with series. So the alternating harmonic series is going to behave a bit differently because, of course, we're switching sign every time. So what's going on here? So we have 1 minus 1/2 plus 1/3 minus 1/4 and so on. So let's go ahead and look at the first few partial sums here. So our S1 is going to be 1, of course. Our S2 is going to be 1 minus 1/2, so 0.5. S3, we're going to add 1/3, so this is about 0.833 and so on. S4, we subtract 1/4, so 0.25 away, we're going to get 0.583. And let's just do one more because it's easy to add 1/5. So we add 0.2 and get 0.783. So if we look at this on our graph here, it's going to look something like this. And you can kind of see what's going on. We have sort of this line that's going down the middle here, where our partial sums are basically alternating which side, because we're subtracting and then adding, alternating which side of this line they're on, but getting closer and closer to this line. And so you can kind of see why you think this should converge. And it turns out that it does. And it actually converges to the natural log of 2, which, by no means are you supposed to eyeball that there. It's something we're actually going to come back to a bit later. So what we just saw was an example where we could apply the alternating series test. So this only applies to series first that are, of course, alternating, but where not only are the terms positive for our an, but also decreasing and going to 0. Okay, and so in that specific case, we know that the alternating series, whether it starts with a positive or negative term, will converge. So again, let's look at some examples. So this one that we just did is one where this is true. right? So in this case, 1 over n is our an. This is always positive. Yep. It's decreasing, right? Every time n increases, 1 over n decreases. So, yep. And the limit as n approaches infinity of 1 over n is 0. And so it satisfies all three criteria, and thus, by the alternating series test, this series converges. Now, it's important to note here that it only says that it converges. It does not say what it converges to. So it's not by the alternating series test that we know this goes to the natural log of 2. That requires a bit more work. All right, so let's start with this example. Let's actually start this at k equals 1 because adding 0 is kind of useless. So here we don't have an an, but rather an ak, which is k over 2k plus 1. So this is clearly positive, always. Is it decreasing? So, I mean, you could use kind of some intuition here and say, okay, I've got slope 2 on the bottom, slope 1 on top, and so my bottom is growing faster, and thus this is decreasing. You could also use the quotient rule and actually find the derivative, show that this is negative, but this is indeed decreasing. And what about the limit? So the limit here as k approaches infinity of k over 2k plus 1, well, this is actually 1/2. So that's not 0. And so in this case, so we do not fit the third criterion, and thus we can't apply the alternating series test. So again, similar to the test for divergence, which only works one way, right? The test for divergence only tells you if a series diverges. It never can tell you that a series converges. The alternating series test tells you if a series converges, given these criteria, but it can't tell you that if they are not satisfied that it diverges. You just have to do more work. But in this case, I mean, you can simply see that it diverges by the test for divergence, right? So what is the limit of this? So it might help to think about what's really going on. So if the ak terms are going to 1/2 and all you're doing is switching sign every time, then you're basically bouncing between something close to 1/2 and something close to negative 1/2 as you keep going. And so the terms themselves do not go to 0, and thus the test for divergence says this series diverges. On the other hand, what if we switch it just ever so slightly here and do negative 1 to the k times k over 2k squared plus 1? So in this case, same reasoning. Our ak is always positive. It is always decreasing. In this case, it's decreasing even faster, right? Because our denominator grows faster. And what is the limit as k approaches infinity of ak? Well, here we have a k over 2k squared plus 1, right? And so the bottom is growing faster. And so you could either use L'Hopital's rule, you could use just kind of a basic analysis that we did in Calc 1 to determine that this limit is indeed 0. And so this guy does converge by the alternating series test. So for your first exercise, I want you to take a look at this series. First of all, determine if this series is alternating or not. If you determine that it is, then we should be able to put it in alternating series form. And so I want you to find the an that would put it in this form, and then determine whether it converges or diverges, and potentially using the alternating series test there. So the last thing we're going to talk about is absolute and conditional convergence of series. So the definitions are actually fairly straightforward. So we say that a series converges absolutely if the sum of the absolute values of each term converges, right? So you're just taking the series and turning all of the terms positive, and you see if that converges or not. And it converges conditionally if the series you have converges, but if you take the absolute value of each term and add them up, it diverges. So we've already seen a few examples. So first one, the series negative 1 to the n plus 1 times 1 over n, right? The alternating harmonic series. This one converges conditionally, right, we showed via the alternating series test that it converges, but we know that if you take the absolute value of each term, which basically just takes away all the minus signs, then you just have the harmonic series, which of course we know diverges, and thus the original converges conditionally. So for that geometric series, right, -1/2 to the n, so this is alternating, and this one converges absolutely, right? Why? Well, again, what's going to happen when you take the absolute value of each term? So you're just going to get this negative going away, right? The -1 to the n in there just becomes a times 1 every time. And so you just get the geometric series 1/2 to the n. And for the same reason, right, that the absolute value of r is less than 1, this guy converges. And so this guy converges absolutely. So it turns out that series which converge absolutely actually have a really nice property in that you can rearrange the terms however you like. You can reorder your ANs however you like, and the series will still always converge to exactly the same number. Right, so for instance, we're actually going to use that in class to show that the alternating harmonic series converges to the natural log of 2. So that is actually a reason why these definitions kind of make sense to introduce. There actually is a distinction, but those that converge absolutely have this other nice property that those which converge conditionally do not. All right, and so for your second exercise, I want you to take a look at this alternating series and determine whether it diverges, converges conditionally, or converges absolutely. All right, thank you for watching.